The story of the universe begins with the Big Bang, an event that marks the origin of everything we know: space, time, matter, and energy. Approximately 13.8 billion years ago, the entire cosmos emerged from an infinitely hot, dense state known as a singularity. This wasn't an explosion in space, but rather the rapid expansion of space itself, stretching from a point smaller than an atom to vast scales and fractions of a second. The Big Bang Theory, first proposed in the 1920s by Georges Lemaitre and later supported by Edwin Hubble's observations of expanding galaxies, explains how the universe evolved from this primordial state. Hubble discovered that distant galaxies are receding from us, with their light redshifted, stretched to longer wavelengths due to the expansion. This redshift increases with distance, indicating the universe is growing larger over time. Rewinding this expansion leads back to a hot, dense beginning. In the earliest moments, known as the Planck epoch, up to 10^3 seconds after the Big Bang, physics as we know it breaks down. Quantum gravity effects dominate, and general relativity and quantum mechanics fail to unify. We lack a complete theory here, but speculative ideas like string theory or loop quantum gravity attempt to describe this era. By 10^3 seconds, cosmic inflation, a brief period of exponential expansion, likely occurred. Proposed by Alan Guth in 1980, inflation solves key puzzles: why the universe appears flat and uniform, the horizon problem, and why large-scale structures exist despite vast separations. During inflation, the universe grew by at least 10^2 times in 10^3 seconds, smoothing out irregularities while quantum fluctuations seeded future galaxies. Post-inflation, the universe entered the radiation-dominated era. Particles and antiparticles annihilated, leaving a slight excess of matter, about 1 part in a billion, over antimatter, explaining why we exist. By 1 second after the Big Bang, temperatures dropped to 10 billion Kelvin, allowing quarks to form protons and neutrons. Big Bang nucleosynthesis, occurring in the first 3 minutes, forged light elements, about 75% hydrogen, 25% helium, and traces of deuterium and lithium. These abundances match observations precisely, providing strong evidence for the theory. Around 380,000 years later, the universe cooled to 3,000 Kelvin. Electrons combined with nuclei to form neutral atoms in the recombination era, making the universe transparent. Photons decoupled, streaming freely as the cosmic microwave background, CMB, radiation, a faint glow at 2.725 Kelvin today, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. The CMB is remarkably uniform, but shows tiny anisotropies, 1 part in 100,000. These fluctuations, mapped by satellites like COBE, 1992, WMAP, 2001 to 2010, and Planck, 2009 to 2013, reflect density variations amplified by inflation. Recent ground-based efforts, like the Atacama Cosmology Telescope, ACT, have refined these maps, confirming the Standard Model's 6 parameters: age, composition, and expansion rate. The CMB also reveals polarization patterns, including potential B modes from primordial gravitational waves, direct evidence of inflation. While early claims were confounded by dust, ongoing searches continue. Evidence supporting the Big Bang is robust. Galactic redshift, universally observed expansion, element abundances, precise matches from nucleosynthesis, CMB existence and properties, blackbody spectrum, and anisotropies. Yet challenges persist. The Hubble tension, a discrepancy in the expansion rate, Hubble constant, remains unresolved as of 2026. Early universe CMB data, e.g., Planck, yield 67 km/s/MPC, while local measurements, supernovae, Cepheids, give 73 km/s/MPC. Recent 2025 results from ACT's final data, quasar lensing, and other methods strengthen this 5 sigma tension, ruling out many extensions to the standard lambda CDM model. This suggests possible new physics, varying dark energy, exotic particles, or modified gravity. Other recent developments include proposals linking gravitational waves directly to structure formation, bypassing traditional inflation, and theoretical work on axions and fusion reactors, potentially tying to post-Big Bang dark matter. The Big Bang isn't the absolute beginning. It describes evolution from a hot, dense state. What preceded it? Eternal inflation, a quantum bounce, or multiverse? Remains speculative. Upcoming missions like Euclid and Roman Space Telescope may probe further. In essence, the Big Bang birthed a dynamic, evolving universe from simplicity to complexity, from quantum foam to atoms, stars, galaxies, and life. It stands as cosmology's cornerstone, continually refined by observations, yet hinting at deeper mysteries awaiting discovery. Imagine standing on Earth, gazing at distant galaxies billions of light years away. Those galaxies are not just sitting still in the vastness of space. They are moving away from us. And the farther they are, the faster they recede. This remarkable discovery reveals that the universe itself is expanding, stretching the fabric of space like a balloon being inflated. Every point in the cosmos moves away from every other point, with no single center to the expansion. This idea traces back to the 1920s, when Edwin Hubble analyzed the light from distant galaxies. He noticed that their spectral lines were shifted toward longer, redder wavelengths, a phenomenon called redshift. The greater the distance to a galaxy, the greater the redshift, meaning the faster it is moving away. Hubble formulated what is now known as Hubble's law. The recessional velocity of a galaxy is proportional to its distance from us. This relationship is expressed as v equals h times d, where v is velocity, d is distance, and h is the Hubble constant, the current rate of expansion. Hubble's initial estimate placed h around 500 kilometers per second per megaparsec, implying a very young universe. Over decades, refinements using better telescopes and distance indicators lowered this value dramatically. Today, as of early 2026, measurements converge on values between roughly 67 and 74 kilometers per second per megaparsec, though persistent discrepancy, known as the Hubble tension, continues to challenge cosmologists. The expansion means that in the past, the universe was smaller, denser, and hotter, leading directly back to the Big Bang. Rewinding the clock about 13.8 billion years takes us to that extraordinarily compact state. But the expansion is not uniform over time. In the early universe, gravity from matter slowed the expansion. Then, surprisingly, around 9 billion years after the Big Bang, or about 5 billion years ago, the expansion began to accelerate. This acceleration was one of the most shocking discoveries in modern cosmology. In the late 1990s, 2 independent teams studying distant type Ia supernovae, exploding stars that serve as standard candles for measuring cosmic distances, found that these supernovae appeared fainter than expected. Fainter meant farther away, implying the universe had expanded more than predicted in recent epochs. Rather than slowing due to gravity, the expansion was speeding up. The culprit behind this acceleration is dark energy, a mysterious repulsive force that permeates space. Dark energy acts like negative pressure, pushing galaxies apart on large scales. In the standard model of cosmology, known as lambda CDM, dark energy is represented by the cosmological constant, lambda, a fixed energy density inherent to empty space itself, as proposed by Einstein. This model posits that dark energy makes up about 68 to 70% of the universe's total energy content today, with dark matter at around 25% and ordinary matter just 5%. Dark energy dominates on the largest scales. Overwhelming gravities pull between distant galaxy clusters. Without it, the universe would eventually collapse under its own gravity or coast to a slow halt. With a constant dark energy, the acceleration continues indefinitely, leading to a future where galaxies recede beyond our observable horizon, leaving a cold, isolated Milky Way in an ever-emptier cosmos. But recent observations are challenging this picture of a constant dark energy. Data from the Dark Energy Spectroscopic Instrument, or DESI, released in 2025, mapped millions of galaxies and quasars, tracing baryon acoustic oscillations, frozen ripples from the early universe that act as a cosmic ruler. Combined with cosmic microwave background data and supernova surveys, these results hint that dark energy may not be constant but evolving, weakening over time. Some analyses suggest the universe's acceleration peaked in the past and is now slowing, entering a phase of deceleration. If confirmed, this would mean dark energy density decreases as the universe grows, altering predictions for its ultimate fate. No longer an eternal acceleration toward isolation, the cosmos might stabilize or even recollapse far in the future. This evolving dark energy could also address the Hubble tension. Early universe measurements, primarily from the cosmic microwave background by emissions like Planck, yield H around 67.4 kilometers per second per megaparsec. Local measurements, using Cepheid variables, type I supernovae, and the cosmic distance ladder, often give higher values, around 73 to 74. Independent methods like gravitational lensing time delays or surface brightness fluctuations sometimes align with a higher figure, deepening the mystery. As of January 2026, the tension persists at around 5 sigma significance in many analyses, suggesting possible new physics beyond the standard model. Proposals include early dark energy that dissipated quickly, modified gravity theories, or inaccuracies in distance calibrations. Upcoming data from the Vera-C, Rubin Observatory, the Euclid Space Mission, and the Nancy Grace Roman Space Telescope promise to map billions more objects, refining expansion history and testing whether dark energy truly varies. Measuring expansion precisely requires multiple independent probes. Type I supernovae remain key, but corrections for host galaxy properties and stellar evolution biases are crucial. Gravitational waves from merging neutron stars offer standard sirens, distance and velocity in one event. Megaparsec scale structures, like galaxy clusters and voids, provide additional checks. The expanding cosmos is not static. It evolves dynamically. From the initial Big Bang push through matter-dominated slowdown to dark energy-driven acceleration, and perhaps now a subtle shift, the universe's growth tells the story of its composition and fate. Understanding cosmic expansion unlocks secrets of fundamental physics, the nature of gravity, the quantum vacuum, and forces yet unknown. As we peer deeper with ever more powerful instruments, the universe reveals its history etched in redshifted light. The expansion is ongoing, carrying galaxies farther apart every moment. Yet questions abound. Will acceleration continue forever? Is dark energy truly constant, or does it fade? Resolving these could redefine our place in an ever-changing cosmos. In this journey through the universe, the expanding cosmos reminds us that space itself is alive, stretching the boundaries of reality. What began as a hot, dense plasma has become a vast tapestry of structures, all drifting apart in a grand, accelerating dance, perhaps one that is only now beginning to change its rhythm. Stars are the luminous hearts of the universe, the furnaces where matter is forged and energy is born. Without stars, there would be no galaxies, no planets, and no life as we know it. They are the fundamental units that organize the cosmos on vast scales, gathering in their billions and trillions to form the spiral arms, elliptical clouds, and irregular shapes we recognize as galaxies. A star begins its life inside vast clouds of cold gas and dust called molecular clouds or nebulae. These clouds, often spanning dozens or hundreds of light years, are mostly hydrogen with traces of helium and heavier elements. Gravity slowly pulls denser regions together. When a fragment collapses under its own weight, it forms a protostar, a hot, dense core surrounded by a spinning disk of material. As the core contracts, temperature and pressure rise dramatically. When the center reaches about 10 million degrees Kelvin, nuclear fusion ignites. Hydrogen atoms smash together to form helium, releasing tremendous energy in the process. The star is born, and its outward radiation pressure balances the inward crush of gravity, establishing a long period of stability. Our Sun is a typical main sequence star, halfway through its 10 billion year life. It fuses hydrogen in its core, producing the light and heat that make Earth habitable. Stars come in a wide range of masses, from about 1/10 the mass of the Sun up to more than 100 times its mass. Mass is the single most important factor determining a star's life story. Low-mass stars burn their fuel slowly and live for tens or hundreds of billions of years. High-mass stars burn furiously and exhaust their fuel in just a few million years. The Hertzsprung-Russell diagram, developed in the early 20th century, reveals the patterns in stellar evolution. Most stars lie along the main sequence, a broad band running from hot, bright, massive blue stars in the upper left to cool, dim, low-mass red stars in the lower right. As stars age and exhaust their core hydrogen, they evolve off the main sequence. Sun-like stars swell into red giants, fusing helium into carbon and oxygen in their cores while hydrogen burns in a surrounding shell. More massive stars pass through additional stages, becoming red supergiants and fusing progressively heavier elements, carbon, neon, oxygen, and silicon, in onion-like layers around an iron core. When fusion can no longer produce energy, because iron absorbs rather than releases energy during fusion, the core collapses in seconds. For stars between about 8 and 20 solar masses, this collapse triggers a core collapse supernova, one of the most violent events in the universe. The outer layers are blasted into space at thousands of kilometers per second, enriching the interstellar medium with heavy elements cooked in the star's interior and forged in the explosion itself. The core may become a neutron star, a sphere roughly 20 kilometers across yet more massive than the Sun, with density comparable to an atomic nucleus. If the progenitor is heavier still, the core collapses beyond the neutron star stage into a black hole. Low and intermediate mass stars like our Sun end more quietly. After the red giant phase, they shed their outer envelopes in beautiful planetary nebulae, leaving behind a white dwarf, a hot, Earth-sized ember supported by electron degeneracy pressure. White dwarfs slowly cool over billions of years, eventually becoming black dwarfs. though the universe is not yet old enough for any to have fully faded. Stars are not born in isolation. They form in clusters ranging from a few dozen members to millions. Open clusters, like the Pleiades, contain a few thousand young, bright stars loosely bound by gravity. Massive globular clusters, orbiting the halos of galaxies, hold hundreds of thousands of ancient stars packed into a sphere just 100 light-years across. These clusters act as snapshots of stellar evolution at different ages and chemical compositions. Stars produce nearly all the elements heavier than helium through nucleosynthesis. The oxygen we breathe, the carbon in our bodies, the silicon in rocks, and the iron in our blood were all forged inside stars over billions of years. When massive stars explode as supernovae, they scatter these elements across space. Subsequent generations of stars form from gas enriched by previous explosions, gradually increasing the metallicity, the fraction of elements heavier than helium in the universe. Our Sun is a third-generation star, born from gas seeded by many earlier stellar deaths. Stars also drive galactic evolution. Their radiation ionizes surrounding gas, creating H2 regions, vast glowing clouds visible in spiral arms. Powerful winds from hot stars and supernova explosions heat and stir the interstellar medium, regulating the rate of future star formation. In starburst galaxies, intense episodes of formation consume gas rapidly, producing thousands of massive stars and supernovae in a short time. Feedback from these events can drive powerful outflows, expelling gas and quenching further star formation. Today, astronomers study stars across the electromagnetic spectrum and beyond. Optical telescopes reveal their colors and spectra, encoding temperature, composition, and motion. X-ray observatories detect accretion onto neutron stars and black holes. Radio telescopes map the cool gas where new stars are born. Gravitational wave detectors like LIGO have opened a new window, catching the mergers of stellar mass black holes and neutron stars, events that produce heavy elements like gold and platinum in spectacular kilonova explosions. Upcoming facilities promise even deeper insights. The James Webb Space Telescope continues to probe the earliest stars. Population 3, massive, metal-free behemoths that formed in the universe's first few 100 million years. Their supernova explosions likely seeded the first heavy elements. The extremely large telescope, with its 39-meter mirror, and the giant Magellan telescope will resolve individual stars in distant galaxies, mapping their motions and compositions in unprecedented detail. The Nancy Grace Roman Space Telescope will conduct massive surveys of Milky Way stars, revealing the galaxy's formation history through precise distances and chemistry. Stars are more than points of light. They are the engines of cosmic evolution, transforming primordial hydrogen into the complex chemistry that allows planets, life, and consciousness to emerge. Every atom in your body, except the hydrogen, was processed inside a star. As Carl Sagan famously said, "We are made of star stuff," a profound truth that connects every living being to the grand cycle of stellar birth, life, and death. Black holes are among the most extreme and enigmatic objects in the universe. They are regions where gravity is so intense that nothing, not even light, can escape their grasp. Born from the deaths of massive stars or through other cosmic processes, black holes challenge our understanding of physics, warp the fabric of space-time, and hold secrets to the fundamental nature of reality. The concept of a black hole emerged from Einstein's general theory of relativity, published in 1915. The first theoretical prediction came just a year later, when Carl Schwarzschild solved Einstein's equations for the gravity around a spherical mass. Dissolution revealed a critical radius, now called the Schwarzschild radius, within which the gravitational pull becomes infinite in classical terms. For mass equal to the Sun, this radius is about 3 kilometers. For Earth, it is merely 9 millimeters. Anything compressed smaller than its Schwarzschild radius becomes a black hole. At the heart of a non-rotating black hole lies a singularity, a point of infinite density where space and time as we know them cease to exist. Surrounding it is the event horizon, the inescapable boundary. Once something crosses this invisible surface, it is lost to the outside universe forever. Time dilation near the horizon is extreme. To a distant observer, an object falling and appears to slow and freeze just above the horizon, its light increasingly redshifted. Black holes form primarily through stellar evolution. When a star at least 20 times more massive than the Sun exhausts its nuclear fuel, its core can no longer support itself against gravity. In a catastrophic core collapse, supernova, the outer layers explode outward while the core implodes. If the remaining core exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, it collapses past the neutron star stage into a black hole. These stellar mass black holes typically range from a few to 100 solar masses. Supermassive black holes, containing millions to billions of solar masses, reside at the centers of most large galaxies, including our Milky Way. Sagittarius A*, the compact radio source at the galactic center, is a 4 million solar mass black hole. How these giants formed remains an open question. Possible pathways include direct collapse of massive gas clouds in the early universe, rapid mergers of smaller black holes, or runaway collisions in dense star clusters. Intermediate mass black holes, between 100 and 100,000 solar masses, bridge the gap. Detections in globular clusters and through gravitational wave mergers have confirmed their existence in recent years. Black holes are not directly visible, but their effects are dramatic. Matter falling toward them forms an accretion disk, swirling superheated gas spiraling inward. Friction heats the disk to millions of degrees, emitting intense X-rays detectable across vast distances. Powerful jets of plasma, accelerated along magnetic fields, can stretch thousands of light years, influencing entire galaxies. In 2019, the Event Horizon Telescope achieved a historic milestone, the first direct image of a black hole. The glowing orange ring around a dark shadow revealed the supermassive black hole in the galaxy M87, 55 million light-years away. 3 years later, in 2022, the same collaboration imaged Sagittarius A*, confirming the predictions of general relativity in these extreme environments. Ongoing improvements to the array continue to sharpen these portraits, probing the dynamics of infalling matter and testing alternative theories of gravity. Gravitational waves have opened another window. In 2015, LIGO detected the merger of 2 stellar mass black holes 30 times the Sun's mass each, 1.3 billion light-years away. The collision released 3 solar masses worth of energy as gravitational waves in a fraction of a second. Since then, dozens of black hole mergers have been observed, along with neutron star collisions. These events reveal the population of black holes in binary systems and their formation channels across cosmic history. Black holes also evaporate. In 1974, Stephen Hawking combined quantum mechanics with general relativity to show that black holes are not completely black. Quantum fluctuations near the event horizon create particle-antiparticle pairs. One falls and while the other escapes, as thermal radiation. This Hawking radiation slowly drains energy from the black hole, causing it to shrink and eventually vanish in a burst of energy. For stellar mass black holes, this process takes longer than the age of the universe. For microscopic primordial black holes, it could be rapid enough to produce detectable gamma rays today. The information paradox arises from Hawking radiation. Classical physics says information falling into a black hole is lost forever, violating quantum mechanics principle that information is conserved. Resolutions may involve subtle correlations in the radiation, holographic principles, or new physics at the horizon. Black holes profoundly affect their surroundings. Active galactic nuclei, powered by supermassive black holes, can outshine entire galaxies. Quasars, distant, brilliant beacons, mark epochs when galaxies grew rapidly by feeding their central black holes. Feedback from these monsters regulates star formation, expelling gas and preventing galaxies from becoming overly massive. Recent discoveries continue to reshape our understanding. In 2024 and 2025, observations of tidal disruption events, stars torn apart by supermassive black holes, revealed unexpected behaviors, including delayed flares and unusual X-ray signatures. Gravitational wave detectors have found surprisingly massive black holes in the upper mass gap, challenging models of stellar evolution. The merger of horizons during black hole collisions produces characteristic ring-down signals, allowing tests of general relativity in the strongest gravitational fields. Deviations could hint at quantum gravity or modified theories. Black holes are more than destroyers. They're cosmic laboratories. They encode the limits of known physics and point toward a deeper unification of gravity and quantum mechanics. Theories like string theory and loop quantum gravity attempt to resolve the singularity, suggesting that space-time remains finite even at the core. As we peer closer with ever-advancing technology, from next-generation gravitational wave observatories like LISA, planned for the 2030s, to enhanced very long baseline interferometry, black holes continue to reveal their secrets. They remind us that the universe harbors environments so extreme that our everyday intuition fails. Yet mathematics and observation guide us toward truth. Nebulae are among the most breathtaking sights in the universe. Vast clouds of gas and dust that glow with ethereal colors against the dark backdrop of space, often spanning tens or hundreds of light years. These interstellar clouds serve as the birthplaces of stars and the final resting places of dying ones. They're the raw material from which new generations of stars and planetary systems emerge, while also painting some of the most iconic images captured by telescopes. The word nebula comes from the Latin for cloud, and early astronomers used it for any fuzzy patch in the sky that wasn't a comet. With improved telescopes, many turned out to be distant galaxies or star clusters, but true nebulae remain diffuse clouds within our own Milky Way or nearby galaxies. They consist primarily of hydrogen and helium, with traces of heavier elements and microscopic dust grains that scatter and absorb light. There are several types of nebulae, each defined by how it interacts with light and nearby stars. Emission nebulae glow with their own light. Ultraviolet radiation from hot, young stars ionizes the surrounding hydrogen gas, exciting electrons to higher energy levels. When the electrons fall back, they emit light at specific wavelengths, producing the characteristic pink and red hues dominated by hydrogen alpha emission. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is the nearest major emission nebula at about 1,344 light-years away. It is a bustling stellar nursery where thousands of stars are forming right now. Reflection nebulae shine by scattering the light of nearby stars. Much like dust in Earth's atmosphere scatters sunlight to make the sky blue. These nebulae appear blue because shorter wavelengths scatter more efficiently. The Witch Head Nebula and the clouds around the Pleiades star cluster are classic examples. Their delicate blue glow revealing the presence of fine dust grains. Dark nebulae absorb visible light from stars behind them, appearing as inky silhouettes against brighter backgrounds. The Horsehead Nebula in Orion, a dramatic pillar of dense gas and dust, is one of the most famous. These regions are often the densest parts of molecular clouds, where star formation is just beginning. Planetary nebulae represent a later stage in stellar evolution. When a sun-like star exhausts its core helium, it swells into a red giant and then sheds its outer layers in a gentle wind. The exposed hot core emits intense ultraviolet light that ionizes the ejected shell, causing it to glow for tens of thousands of years before dispersing. Despite their name, planetary nebulae have nothing to do with planets. Early observers thought their round shapes resembled planetary disks. The Ring Nebula, Helix Nebula, and Cat's Eye Nebula showcase intricate shells, rings, and bipolar outflows shaped by magnetic fields and binary companions. Supernova remnants are the expanding debris clouds left after massive stars explode. The Crab Nebula, remnant of a supernova observed in 1054 AD, is powered by a rapidly spinning neutron star, a pulsar, at its center. Its intricate filaments of ionized gas glow across the spectrum from radio to gamma rays, while synchrotron radiation from high-energy electrons produces a bluish glow. Nebulae are fundamentally stellar nurseries. The vast majority of stars form within giant molecular clouds, cold, dense regions where temperatures drop to just 10 to 20 degrees above absolute zero. Gravity slowly overcomes thermal pressure in overdense pockets, causing collapse. As a cloud fragment contracts, it fragments further into dozens or hundreds of protostars. Observations with infrared and radio telescopes pierce the obscuring dust to reveal embedded young stars still swaddled in their placental cocoons. The pillars of creation in the Eagle Nebula, made famous by the Hubble Space Telescope in 1995 and revisited in stunning detail by the James Webb Space Telescope in 2022, show towering columns of gas resisting erosion by ultraviolet light from nearby massive stars. At their tips, evaporating gaseous globules harbor newborn stars. These pillars illustrate the delicate balance between destructive radiation and gravitational collapse that govern starbirth. Feedback from young stars eventually disrupts their birth clouds. Intense radiation and powerful stellar winds carve bubbles and cavities, while supernova explosions from the shortest-lived massive stars can trigger new rounds of collapse in surrounding gas. This self-regulating cycle controls the overall efficiency of star formation across galaxies. Only a small fraction of a molecular cloud's mass typically turns into stars before the cloud is dispersed. Modern observatories have revolutionized our view of nebulae. The Hubble Space Telescope captured sharp, visible light images revealing fine structure in newborn stars. The Spitzer Space Telescope mapped infrared emission from warm dust and organic molecules. The James Webb Space Telescope, with its unprecedented sensitivity in the mid-infrared, peers deep into obscured regions, revealing previously hidden protostars and the chemistry of complex molecules like polycyclic aromatic hydrocarbons, potential building blocks of life. ALMA, the Atacama Large Millimeter/Submillimeter Array, traces cold gas and dust at millimeter wavelengths, mapping the dynamics of collapsing cores and the disks that will become planetary systems. Recent ALMA observations have detected rotating disks around very young protostars in regions like the Perseus molecular cloud, confirming theories of angular momentum conservation during collapse. Nebulae also host rich chemistry. In cold, dense regions shielded from ultraviolet light, atoms combine on dust-grained surfaces to form molecules. Water, carbon monoxide, ammonia, and even complex organics like methanol and glycolaldehyde. These molecules are released into the gas phase when newborn stars heat their surroundings, seeding the interstellar medium with the raw materials for future planets and potentially life. Some nebulae challenge simple classification. The Carina Nebula, one of the largest and brightest, contains multiple types: emission regions, dark pillars, reflection zones, and the violent aftermath of recent stellar deaths. Eta Carinae, a massively unstable star within it, may soon explode as a supernova, dramatically altering the nebula's appearance. As the universe ages, the supply of cold gas for new nebulae gradually declines. In billions of years, star formation will slow and eventually cease as galaxies exhaust their reservoirs. The magnificent nebulae we see today are a transient phase in cosmic evolution, a brief era when gas clouds collapse, ignite, and sculpt the space around them with light and motion. Our journey through the universe naturally leads us to planets, those diverse worlds orbiting stars, shaping systems with their gravity and chemistry. In our own solar system, 8 planets circle the Sun, from scorching Mercury to frigid Neptune, each a unique testament to how worlds form from swirling disks of gas and dust. Beyond these familiar orbs lie exoplanets, planets orbiting other stars, numbering over 6,000 confirmed as of early 2026. These distant worlds expand our understanding of planetary possibility, revealing environments from hellish lava oceans to potential ocean-covered havens. The solar system begins with the inner terrestrial planets. Mercury, the smallest, endures extreme temperatures swinging from 430 degrees Celsius by day to minus 180 at night. Venus, shrouded in thick carbon dioxide, suffers a runaway greenhouse effect, making it the hottest planet at around 460 degrees. Earth, uniquely blue and alive, balances liquid water, a protective magnetic field, and plate tectonics to sustain complex life. Mars, red and rusty, once hosted rivers and lakes. Today, its thin atmosphere and polar ice caps intrigue us with hints of past habitability. Farther out, the gas giants dominate. Jupiter, the largest, boasts swirling storms like the Great Red Spot and over 90 moons, including icy Europa with its subsurface ocean. Saturn dazzles with intricate rings of ice and rock, while shepherd moons maintain their structure. Uranus and Neptune, ice giants, contain mantles of water, ammonia, and methane ices under hydrogen-helium atmospheres, tilted axes giving them extreme seasons. Dwarf planets like Pluto and the Kuiper Belt reveal icy, geologically active surfaces with nitrogen glaciers and towering water ice mountains. Thousands of smaller bodies, asteroids, comets, and trans-Neptunian objects complete this frozen outer realm. Formation began 4.6 billion years ago from a collapsing solar nebula. Dust grains clumped into planetesimals, then protoplanets. In the hot inner system, only rock and metal survived. Beyond the frost line, ice enabled rapid growth of giant cores that accreted gas envelopes. Exoplanet discovery revolutionized this picture. The first confirmed exoplanet around a sun-like star, 51 Pegasi b, in 1995, shocked astronomers. A Jupiter-mass world orbiting in just 4 days, a hot Jupiter puffed up by stellar heat. Early detections favored massive, close-in planets via radial velocity, measuring stellar wobbles, or transit method, detecting dips in starlight. Today, over 6,000 exoplanets are confirmed, with thousands more candidates. NASA's Kepler and TESS missions drove this explosion, finding thousands via transits. The transit method dominates, revealing sizes. Combined with radial velocity, it yields masses and densities. Exoplanets defy expectations. Hot Jupiters migrate inward through disk interactions or gravitational scattering. Super-Earths and mini-Neptunes, common sizes absent in our system, range from rocky worlds larger than Earth to gaseous subneptunes. Rogue planets, free-floating without stars, number in the billions, ejected during formation. Habitable zones, regions where liquid water could exist, host intriguing candidates. The TRAPPIST-1 system, 40 light-years away, packs 7 Earth-sized planets around a cool red dwarf. 3 in the habitable zone. Tidally locked, they face eternal day on one side and night on the other, potentially stabilizing climates with atmospheres. Proxima Centauri b, just 4.2 light-years away, orbits our nearest stellar neighbor in its habitable zone, though flares from the red dwarf challenge habitability. K2-18b, a super-Earth, sparked debate in 2025 with renewed detections of possible biosignature gases, though contamination remains possible. The James Webb Space Telescope transforms exoplanet study. Its infrared sensitivity pierces atmospheres during transits, revealing compositions via transmission spectroscopy. Starlight filtered through planetary air shows absorption lines of molecules like water, methane, carbon dioxide. JWST confirmed steamy atmospheres on hot worlds and probed cooler ones for habitability signs. 2025 brought exciting discoveries. Young giant planets still forming in protoplanetary disks, eccentric warm Jupiters defying migration models, and a rogue Saturn-mass world drifting alone 10,000 light-years away. Spectra of ultra-short period planets like TOI 561b revealed dense, windy environments. A bizarre carbon-rich world around a neutron star, stretched by gravity into a lemon shape, highlighted extreme possibilities. Diversity astounds. Lava worlds with iron rain, diamond planets under crushing pressure, ocean worlds beneath icy shells. Artistic visions blend science with imagination, depicting jungle-covered super-Earths or glassy blue giants. Upcoming missions promise more. ESA's Plato, launching in 2026, targets Earth-like planets around Sun-like stars. Ariel will survey hundreds of exoplanet atmospheres. Ground-based, extremely large telescopes will directly image rocky worlds, measuring their spectra for oxygen or ozone, potential life signs. Galaxies are the grand architectural wonders of the universe. Vast, self-gravitating systems containing billions to trillions of stars, along with gas, dust, dark matter, and often a central supermassive black hole. They are the islands of light in an otherwise dark and empty cosmos, separated by millions of light-years of near vacuum. Each galaxy is a dynamic ecosystem where stars are born, evolve, and die over billions of years, shaping the structure and evolution of the universe itself. Our own Milky Way is a barred spiral galaxy, roughly 100,000 light-years across, containing about 300 billion stars. From inside, it appears as a faint band of light arching across the night sky. Spiral arms wind outward from central bar, rich in gas and sites of active star formation. A supermassive black hole of 4 million solar masses sits quietly at the core. Surrounding the visible disk is an extended halo of old stars and globular clusters, enveloped by a much larger sphere of invisible dark matter that provides most of the galaxy's gravitational binding. Galaxies come in three main morphological types, as classified by Edwin Hubble in his 1926 tuning fork diagram. Spiral galaxies like the Milky Way and Andromeda feature flat, rotating disks with prominent arms traced by bright young stars and glowing nebulae. Barred spirals have a central rectangular bar of older stars, from whose ends the arms emerge. About two-thirds of nearby bright spirals show bars. Elliptical galaxies range from nearly spherical giants to flattened, football-shaped systems. They contain mostly older, low-mass stars with little gas or dust, giving them a smooth, featureless appearance and reddish color. Star formation has largely ceased, making ellipticals cosmic retirees. Irregular galaxies lack clear symmetry. Some, like the Large and Small Magellanic Clouds, are small, gas-rich systems distorted by gravitational interactions with larger neighbors. Others result from mergers that scramble orderly structures into chaotic shapes. A fourth category, lenticular galaxies, bridges spirals and ellipticals. They have disks, but depleted gas reservoirs and minimal spiral arms, often appearing as faded spirals that have run out of fuel for new stars. Galaxies do not form in isolation. They cluster together under gravity. Our local group contains over 70 galaxies, dominated by the Milky Way and Andromeda, which are on a collision course in about 4.5 billion years. The local group itself is part of the much larger Virgo supercluster, a filamentary structure stretching over 100 million light-years, containing thousands of galaxies. On even grander scales, the universe is organized into a cosmic web of filaments, walls, and vast voids, with galaxy clusters marking the densest nodes. Galaxy formation began shortly after the Big Bang. Tiny density fluctuations in the primordial plasma, amplified by inflation, grew under gravity as the universe expanded and cooled. By a few hundred million years after the Big Bang, the first galaxies, small, irregular systems rich in pristine hydrogen and helium, ignited their first stars. These population 3 galaxies were metal-poor and short-lived, their massive stars exploding and seeding the intergalactic medium with heavier elements. Over time, galaxies grew through 2 main processes: hierarchical merging and gas accretion. Smaller systems collided and coalesced into larger ones, triggering bursts of star formation as gas clouds compressed. Cold gas streams from the cosmic web also fed steady, quieter growth. The peak of galaxy assembly occurred around redshift 2, when the universe was about 3 billion years old, marking the height of cosmic star formation. Today, the star formation rate across the universe has declined dramatically. Massive galaxies formed most of their stars early, quenching as feedback from supernovae and active black holes expelled or heated remaining gas. Smaller galaxies continue forming stars at lower rates. Environmental effects also play a role. Galaxies falling into dense clusters lose gas through ram pressure stripping or tidal interactions, turning blue, star-forming spirals into red, passive ellipticals. The most luminous galaxies are often starbursts, driven by mergers or intense gas inflows. Ultraluminous infrared galaxies glow fiercely in the infrared as dust obscures and re-radiates the light of millions of newborn stars. At the extreme end, quasars shine with the power of trillions of suns, fueled by supermassive black holes accreting at prodigious rates during galaxy mergers. Modern surveys have mapped millions of galaxies across cosmic time. The Sloan Digital Sky survey revolutionized our view of the nearby universe, while deep fields from Hubble And now, the James Webb Space Telescope reveal the distant early cosmos. JWST's infrared vision pierces dust and looks back to when the first galaxies formed, spotting surprisingly bright and massive systems just a few 100 million years after the Big Bang, challenging models of early structure formation. Recent discoveries include green pea galaxies, compact, vigorously star-forming systems that resemble the young universe, and jellyfish galaxies with trailing tentacles of ionized gas stripped by cluster winds. Oddities like ultra-diffuse galaxies, as large as the Milky Way, but with only a fraction of the stars, hint at dark matter's dominant role in shaping structure. Galaxies evolve dramatically through interactions. Mergers can transform spirals into ellipticals, funnel gas to the center to feed black hole growth, and trigger rings or tidal tails of stars. The antennae galaxies, caught mid-collision, showcase this violence with brilliant starburst regions along overlapping arms. Simulations predict that the Milky Way-Andromeda merger will eventually produce a giant elliptical dubbed Milkomeda. Dark matter halos anchor galaxies gravitationally. Visible matter traces only a small fraction of the total mass. The rest is invisible dark matter, detected through its gravitational influence on stellar motions and galaxy clusters. Hot gas in clusters, emitting X-rays, provides another mass probe, confirming dark matter's dominance. As the universe ages and expands, galaxies grow increasingly isolated. Dark energy pushes clusters apart, halting new mergers on large scales. In the distant future, most galaxies will fade as star formation ceases, leaving behind dead relics in an ever-emptier void. The universe we see, stars, galaxies, nebulae, planets, is only a tiny fraction of what truly exists. Roughly 95% of the cosmos is invisible, made of two mysterious components, dark matter and dark energy. These unseen forces dominate the universe's mass and energy budget, shaping its structure, expansion, and ultimate fate, yet we still do not know exactly what they are. Dark matter makes up about 27% of the total energy content of a universe today. It does not emit, absorb, or reflect light, rendering it invisible to telescopes across all wavelengths. We detect its presence only through gravity. Its gravitational pull influences the motion of stars, the rotation of galaxies, and the way light bends around massive objects. The first strong evidence came in the 1930s from Fritz Zwicky's study of the Coma Cluster. He calculated that the galaxies moved far too quickly for the visible mass alone to hold the cluster together. Something unseen provided the extra gravity. Decades later, in the 1970s, Vera Rubin measured the rotation curves of spiral galaxies. Stars at the edges orbit just as fast as those near the center, contrary to expectations from visible matter alone. Flat rotation curves require an extended halo of invisible mass surrounding each galaxy, far beyond the visible disk. Today, gravitational lensing offers dramatic proof. Massive galaxy clusters bend light from distant background galaxies, creating distorted arcs and multiple images. The amount of bending reveals total mass, and maps show that most of the mass sits in a smooth, extended halo, not in the visible galaxies. The Bullet Cluster provides even clearer evidence. During a collision between two clusters, hot X-emitting gas slowed down due to friction, while the gravitational mass, tracked by lensing, continued straight through, separating from the visible matter. This separation shows that dark matter interacts gravitationally, but not electromagnetically. On cosmic scales, the pattern of galaxy clustering matches predictions only if dark matter is present. The cosmic microwave background shows tiny temperature fluctuations that grew into today's large-scale structure. Simulations reproduce the observed web of filaments, walls, and voids only when dark matter is included as a cold, slow-moving component that clumps under gravity. What could dark matter be? The leading candidate is a new type of elementary particle, weakly interacting in massive WIMPs, that formed in the early universe and remain stable today. Other possibilities include axions, sterile neutrinos, or even primordial black holes. Decades of direct detection experiments, deep underground detectors searching for rare collisions with ordinary matter, have set increasingly tight limits but found no clear signal. Indirect searches look for annihilation products like gamma rays or positrons in space. Collider experiments at the Large Hadron Collider continue hunting for production of dark matter particles in high-energy collisions. So far, the null results push the simplest WIMP models into tighter corners, prompting exploration of lighter or more exotic candidates. Dark energy, accounting for about 68% of the universe, is even more mysterious. It drives the accelerated expansion discovered in 1998. Unlike ordinary matter or dark matter, which slow expansion through gravity, dark energy exerts repulsive pressure, pushing galaxies apart faster over time. The simplest explanation is Einstein's cosmological constant, a fixed energy density inherent to empty space itself. Quantum field theory predicts vacuum energy, but the calculated value is infamously larger than observed by about 120 orders of magnitude, a problem known as the cosmological constant puzzle. Despite this mismatch, the constant fits observations remarkably well. Alternative ideas include quintessence, a dynamic scalar field that evolves slowly over cosmic time, or modifications to general relativity on large scales. Recent data hint that dark energy may not be perfectly constant. Measurements from the Dark Energy Spectroscopic Instrument, combined with supernova surveys and cosmic microwave background results, suggest the density of dark energy might have been slightly higher in the past and is now declining. If confirmed, this would rule out a pure cosmological constant and open the door to new physics. The interplay between dark matter and dark energy shapes the universe's destiny. In the Standard Model, dark energy dominates forever, stretching space so rapidly that distant galaxies eventually disappear beyond our cosmic horizon. The universe grows colder and emptier, ending in a state of eternal isolation. If dark energy weakens, expansion could slow, halt, or even reverse into a big crunch far in the future. Understanding these invisible components requires multiple probes. Galaxy surveys map how dark matter clusters and how dark energy affects large-scale structure. Weak gravitational lensing measures the distribution of dark matter across billions of light years. Type I supernovae serve as standard candles to track expansion history. The cosmic microwave background encodes early fluctuations that seeded dark matter halos. Gravitational wave observatories may one day detect signatures from dark matter interactions or exotic dark energy models. Upcoming missions promise major advances. The Euclid Space Telescope, launched in 2023, is now delivering wide-field, weak lensing, and galaxy clustering data to measure dark energy's equation of state with unprecedented precision. The Vera-C, Rubin Observatory's legacy survey of space and time, will image billions of galaxies, tracing dark matter's influence over cosmic time. The Nancy Grace Roman Space Telescope will combine high-resolution imaging with wide surveys, probing both dark matter and dark energy simultaneously. Theoretical work continues to bridge gaps. Some models link dark matter and dark energy, through a single field or modified gravity theories. Others explore extra dimensions or quantum gravity effects that could explain both phenomena. Dark matter and dark energy remind us how much of reality lies beyond our senses. They dominate the universe, yet remain hidden, challenging our theories and forcing us to rethink fundamental physics. They sculpted the cosmic web, determined the fate of galaxies, and set the stage for the emergence of stars, planets, and life. The question of whether we are alone in the universe has captivated humanity for centuries. Today, it stands at the forefront of modern science, driven by discoveries of thousands of exoplanets, advances in biochemistry, and missions exploring our own solar system. The search for extraterrestrial life, known as astrobiology, seeks not just intelligent civilizations, but any form of life, from simple microbes to complex organisms. It combines astronomy, biology, planetary science, and chemistry to identify habitable environments and detect potential biosignatures. Life, as we know it, requires three key ingredients: liquid water, a source of energy, and organic molecules capable of building complexity. Earth's life thrives in diverse extremes, from deep-sea hydrothermal vents to acidic hot springs, suggesting that life elsewhere might adapt to conditions once thought hostile. This resilience expands the range of worlds we consider potentially habitable. Within our solar system, several bodies stand out as prime targets. Mars, with evidence of ancient rivers, lakes, and a thicker past atmosphere, may have hosted microbial life billions of years ago. Today, subsurface aquifers or briny flows could harbor extremophiles. NASA's Perseverance rover, exploring Jezero crater since 2021, has collected samples rich in organic molecules and potential biosignatures. The Mars Sample Return mission, planned for the 2030s, aims to bring these rocks back to Earth for detailed analysis. Europa, Jupiter's ice-covered moon, hides a global ocean beneath its cracked surface, kept liquid by tidal heating from Jupiter's gravity. Hydrothermal vents on the seafloor, analogous to Earth's deep-sea ecosystems, could provide energy and nutrients. The Europa Clipper mission, arriving in 2030, will map the ice shell and search for plumes of water vapor erupting into space, offering a chance to sample the ocean without drilling. Enceladus, a smaller Saturn moon, actively spews water plumes from its south pole, containing salts, organic molecules, and silicon nanoparticles suggestive of hydrothermal activity. Cassini's flybys in the 2000s and 2010s detected complex organics and hydrogen, potential fuel for microbes. Future missions, including proposed life detection orbiters or landers, could target these plumes directly. Titan, Saturn's largest moon, boasts thick atmosphere and stable lakes of liquid methane and ethane. Its chemistry produces complex organics, and a subsurface water ocean may exist. The Dragonfly rotorcraft mission, launching in 2028 and arriving in 2034, will hop across Titan's surface, analyzing prebiotic chemistry that might mirror Earth's early steps toward life. Beyond the solar system, the explosion of exoplanet discoveries has transformed the search. Most stars host planets and red dwarfs, the most common stellar type, often have rocky worlds in their habitable zones. Systems like TRAPPIST-1, with 7 Earth-sized planets, offer multiple chances for liquid water. Though tidally locked, atmospheric circulation could distribute heat, creating temperate regions. Detecting life on exoplanets relies on biosignatures, atmospheric gases or surface features produced by biological processes. Oxygen, produced on Earth by photosynthesis, is a strong candidate, but abiotic processes can mimic it. Methane combined with oxygen or ozone suggests a biological imbalance, as these gases react quickly without constant replenishment. The James Webb Space Telescope has begun characterizing exoplanet atmospheres, detecting water vapor, carbon dioxide, and methane on several worlds. In 2025, refined analyses of K2-18b, a super-Earth in the habitable zone, revealed tentative hints of dimethyl sulfide, a gas produced by marine plankton on Earth, though alternative explanations remain. Future telescopes will push further. The Extremely Large Telescope and Giant Magellan Telescope, coming online in the late 2020s and early 2030s, will directly image rocky exoplanets and analyze reflected light for oxygen, ozone, and vegetation-like surface signatures. The Habitable Worlds Observatory, a NASA flagship concept for the 2040s, aims to image dozens of Earth-like planets and search for definitive biosignatures. The search for extraterrestrial intelligence, SETI, focuses on technological civilizations. Radio telescopes scan for narrowband signals that might indicate artificial transmitters. The Allen Telescope Array and China's FAST Telescope monitor millions of stars. Breakthrough Listen, launched in 2015, has expanded searches into optical and infrared wavelengths, looking for laser pulses or waste heat from advanced civilizations. No confirmed signals have been found, but the effort continues, now augmented by machine learning to sift vast data streams. The Fermi paradox asks, if the galaxy is old and vast, where is everybody? Possible answers range from the rarity of intelligent life to self-destruction or deliberate silence. Some suggest advanced civilizations might use communication methods we cannot yet detect, or that we are simply early in cosmic history. Recent developments keep the field dynamic. Laboratory experiments recreate prebiotic chemistry under Titan-like conditions, producing amino acids and nucleotide precursors. Studies of Earth's deep subsurface biosphere reveal microbes living kilometers down, expanding models for life on icy moons or Mars. Discoveries of phosphine in Venus's clouds in 2020 sparked debate, later attributed to sulfur chemistry, but highlighted how even hostile atmospheres might harbor aerial life. As of early 2026, no definitive evidence of extraterrestrial life exists, but the search has never been more promising. Each mission and observation narrows the possibilities, building a clearer picture of how common or rare life might be. The search for life beyond Earth is ultimately a search for perspective. Finding even microbial life elsewhere would confirm that biology is a cosmic phenomenon, not a singular accident. Discovering complex or intelligent life would reshape philosophy, religion, and our sense of place. Even a continued absence of detection teaches us about the conditions required for life to emerge and persist. In this vast universe of billions of galaxies and trillions of planets, the ingredients for life appear widespread. Water is common in comets and moons. Organic molecules rain down on young worlds, and energy flows from stars, tides, and chemistry. Whether these ingredients have mixed into living systems elsewhere remains one of the greatest open questions in science. A question we are now, for the first time, equipped to answer. The search continues, driven by curiosity and the profound desire to know whether, in the silence of the cosmos, there are other voices calling out across the stars. Humanity's future, exploring and colonizing space. Humanity stands at the threshold of becoming a multi-planetary and, eventually, interstellar species. The drive to explore and settle space is rooted in curiosity, survival, and the desire to secure our long-term future. From the first steps on the moon to ambitious plans for Mars and beyond, space exploration is evolving from government-led missions to a collaborative effort involving private companies, international partnerships, and visionary entrepreneurs. The next chapters of our cosmic journey promise profound technological, societal, and philosophical transformations. The modern space age began with Sputnik in 1957, followed by Yuri Gagarin's orbit and Apollo 11's lunar landing in 1969. After decades focused on low Earth orbit, space shuttles, the International Space Station, and robotic probes to planets and comets, a new era emerged in the 2010s. Private companies like SpaceX, Blue Origin, and Rocket Lab dramatically reduced launch costs through reusable rockets. Falcon 9 landings became routine, and Starship, the largest and most powerful rocket ever built, began flight testing, aiming for full reusability and payloads of over 100 tons to orbit. By early 2026, NASA's Artemis program has returned astronauts to the lunar vicinity with Artemis I, 2022, and Artemis II, 2025 crewed flyby. Artemis III, targeted for late 2026 or 2027, will land the first woman and first person of color on the moon's south pole, using SpaceX's human landing system. The Gateway Lunar Orbit Station is under assembly, serving as a staging point for deeper missions. These efforts lay groundwork for sustained lunar presence, mining water ice for fuel, building habitats, and conducting science in permanently shadowed craters. Mars looms as the next great horizon. SpaceX's Starship is designed to carry crews and cargo there, with founder Elon Musk outlining plans for an uncrewed mission as early as 2028 and crewed landings in the 2030s. NASA's Mars sample return remains in planning, while China's Tianwen missions and the joint ESA-Roscosmos ExoMars rover, delayed but resuming, probe the red planet's habitability. Long-term visions include terraforming, warming Mars, thickening its atmosphere, and introducing liquid water, though such mega-engineering lies centuries away. Beyond government timelines, private initiatives accelerate progress. Vast Space, Relativity Space, and Stoke Space develop new launch vehicles. Orbital Reef and Starlab commercial space stations aim to replace or complement the ISS after its retirement around 2030. Axiom Space already attaches private modules to the ISS, hosting crewed missions. Colonization requires solving immense challenges. Radiation beyond Earth's magnetic field poses cancer and cognitive risks. Solutions include better shielding, pharmaceuticals, and artificial magnetic fields. Microgravity weakens bones and muscles. Countermeasures involve exercise, centrifugal habitats, and advanced medicine. Psychological isolation demands careful crew selection and robust communication. Life support systems must recycle air, water, and waste near perfectly. In situ resource utilization, extracting oxygen from lunar regolith or Martian CO2, will reduce dependence on Earth resupply. 3D printing with local materials can build habitats. Experiments on the ISS already print tools and medical devices. Energy is critical. Solar power works near Earth and on the Moon, but nuclear fission reactors, compact and reliable, offer baseload power for night spans or distant worlds. NASA and DARPA are developing space nuclear propulsion for faster interplanetary transit. Economic drivers are emerging. Asteroid mining promises platinum group metals, water, and construction materials. Helium-3 from the lunar regolith could fuel future fusion reactors, though practical fusion remains decades away. Space tourism, already underway with suborbital flights by Virgin Galactic and Blue Origin, may expand to orbital hotels. International cooperation and competition coexist. The Artemis Accords, signed by over 40 nations, establish norms for peaceful lunar exploration. China and Russia pursue their own International Lunar Research Station. Avoiding conflict while sharing benefits will test global governance. Longer term, the outer solar system beckons. Jupiter's Europa and Saturn's Enceladus offer subsurface oceans. Permanent bases there would study potential life while harvesting resources. Oort cloud comets could supply volatiles for an expanding interplanetary economy. Interstellar travel remains speculative but not impossible. Breakthrough Starshot proposes laser-propelled nanocraft to reach Alpha Centauri in decades. Generation ships or suspended animation arcs could carry humans on centuries-long voyages. Nuclear fusion or antimatter propulsion might one day enable crewed missions to nearby stars. Settling space will change humanity profoundly. Multiplanetary life hedges against Earth-bound catastrophes. Asteroids, pandemics, climate shifts, or nuclear conflict. As Stephen Hawking warned, putting all our eggs in one planetary basket is risky. A self-sustaining Mars settlement, envisioned within a century, ensures species survival. Culturally, space expansion may foster unity or new divisions. Shared challenges could strengthen global cooperation. Resource races could heighten tensions. Ethical questions abound. Who owns lunar or Martian land? How do we protect potential alien life? Should we alter other worlds? Scientific returns will be immense. Low-gravity manufacturing may revolutionize materials and pharmaceuticals. Astronomical observatories on the lunar far side, shielded from Earth's radio noise, could detect faint signals from the early universe or extraterrestrial intelligence. Ultimately, becoming a spacefaring civilization redefines our identity. Earth becomes a cradle we outgrow, not abandon. As we spread across the solar system and perhaps beyond, humanity carries its knowledge, art, and diversity into the cosmos, seeding life and consciousness where none existed before. The journey ahead is daunting, but history shows human ingenuity thrives on great challenges. From fire to flight, each leap expanded our reach. Now, the final frontier awaits, not as escape, but as the next stage of our evolution. In this vast universe we have explored, from the Big Bang's echo to distant galaxies and the search for life, humanity's future lies in stepping outward. The stars are not just to admire, they're destinations. By exploring and colonizing space, we secure our survival, unlock boundless potential, and fulfill the ancient dream of reaching beyond our world. The cosmic story that began 13.8 billion years ago now includes us as active participants, writing the next chapters among the stars.